Okay, welcome everyone to our, is it the 11th webinar in our series? This is, well, first of all, my name is Erica Kuligowski, and I will be your MC for today. This is part of the Human Behavior in Fire's webinar series from the Human Behavior in Fire Permanent Group of the International Association for Fire Safety Science. So we're really excited to be presenting or showcasing two additional early career researchers in our field who will be talking about crowd evacuation. And so we'll have two speakers today, Juraj Kmec, and he will be talking about sensitivity analysis in pedestrian and evacuation modeling. And then second, Yuxin Zhang on how to model evacuation behavior in fire, a coupling numerical approach using CFD and CA models. And we're really excited to have you both here. Thank you so much for presenting on your topic and for sharing your expertise with us today. So a little bit about the Human Behavior in Fire Permanent Group in IAFSS. I am coordinating this alongside with my colleague, Associate Professor Enrico Ronchi from Lund University in Sweden. And so we've been working and leading this group for a couple of years now within IAFSS. And we thank very much Arthur Rohart for his amazing technical support, not just for the webinar series, but really for our group in general. And Arthur is from Lund University, so thank you very much. This is the 11th event of our webinar series. We're really excited about that. And this will be recorded today and posted on our YouTube channel. And Arthur, if you don't mind sharing a link to the YouTube channel, we have all of the other 10 webinars on that YouTube channel for you to take a look if you haven't seen them. And they're on a number of different topics, all relevant to human behavior in fire. So hopefully you'll have a chance to take a look at that if you've missed any in the series. We also have a number of ongoing activities in our group. One of them in particular is developing a research roadmap. And so we've got 4 different task groups working on understanding the research gaps in the field. And we've published 1 paper from that work already. Enrico is leading another task group that is working on a paper at the moment, understanding the obstacles to our research gaps. And then there'll be a final set of work, research report, and hopefully a publication on the research roadmap itself. So please stay tuned. If you haven't already joined our permanent working group, really would love to have you join us. And so Arthur will also put in the chat a link to join our permanent group in IAFSS. And that, if you join, you'll be able to maintain, certainly be updated on what we're doing. Feel free to contribute. So please sign up through the link that Arthur will share in the chat. All right, so our early career researchers on evacuation modeling, so on crowd evacuation. So I just want to read a bit of their bios, and if they would like to say a little bit more about themselves, they can certainly feel free to do that. And then once I'm done, I'll turn it over to Juraj. First, Juraj Kmec is a PhD student at the Czech Technical University in Prague. With a background in computer science, his research focuses on the use of sensitivity analysis and machine learning techniques in pedestrian and evacuation dynamics. I'm really looking forward to your presentation today. Dr. Yuxin Zhang completed her PhD at Tongji University, during which she studied at the University of Edinburgh and Brown University for 2 years. Her research focuses on human-centric response in fire, and she applies data analysis and modeling to predict evacuation procedure and optimize evacuation plans. So thank you both for joining us. I'm going to stop sharing my screen. So I will turn it over to you, Juraj, to please share your screen with us. And just a kind of an overview of how this next hour is going to work, or 50 minutes is going to work. Each speaker will have about 18 minutes, and then that will leave us about 20 minutes for questions. As you are listening to these amazing speeches, please feel free to type your questions in the chat, and then I'll be moderating those at the end of our talks today. And please stay tuned. So this is sort of our last webinar before the summer hits for the northern part of the world. And so we'll certainly be reestablishing some of the webinar series after the summer's over. So stay tuned and for new webinars coming up. So I'll turn it over to you, Juraj, to please share your screen. And I'll let you know if we're going over time, but just maybe around 18 minutes, and then we'll turn it back over to Yuxin. Thank you so much.
Okay, thank you. So I've tried sharing the screen. I'm not sure if you can see it.
Yes,
yeah,
you can see it perfectly. Thank you.
Perfect. So we can get to it. All right. So thank you, Erica, for the introduction and for the opportunity to present some of our research and what we do here at this webinar. I would also want to give a quick shout out to my supervisors, Pavel Hrabak, Hanna Najmanova, and Daniel Vašeta. I believe Hanka is here. And as you can see, the topic for today is sensitivity analysis in pedestrian and evacuation modeling, where I've kind of structured this talk into two segments, where the first one is a bit of an advertisement for sensitivity analysis, an introduction, what is it, and how it's been used in evacuation modeling lately. And the second part will be a case study of a simulated evacuation of a heterogeneous crowd. So we'll have an example of how we can use these methods. All right, so first of all, we should kind of talk about what situation are we in. So we have a black box model, like a simulator or other model where we don't really know what's going on inside, but we can collect data from it. So we have a bunch of inputs here and one or more outputs, and sensitivity analysis can help us answer questions such as which of these inputs are the most important, or which of them are not quite as important, and we can kind of leave them out of the analysis and not lose much information. Or what are some of the kind of interesting parameter ranges where, for example, most of the changes in the output happen, or what parameter combinations lead to quote unquote special outcomes, such as a system failure or failed evacuation, for example. So I have a very quick definition here for you. It is sensitivity analysis is the study of how uncertainty in the output of a model can be apportioned to different sources of uncertainty in the model input. So we're looking at what is the exact effect of each of the inputs. This is often paired with uncertainty analysis, which is simply the quantification of uncertainty in the model output. And I also have a simple example here, which many of you have probably seen at some point, and that's standardized regression coefficients. So if we have a linear model like this, then these least squares coefficients tell us something about how the model behaves with respect to each of the inputs. There's just a small thing that we have to do. We have to standardize them and bring them to a common range, but this can be easily done, and we get a nice, simple sensitivity measure. But there are some more sophisticated methods. One that comes to the mind first for many people is derivatives, right? So basically, we pick a baseline point, like some reasonable parameter values, and we change each of the inputs on some interval, kind of one by one, and see what happens on the output side. And this is called the one-at-a-time approach. And it's a sensitivity measure, but it has some problems, mainly that it depends on the choice of the initial point in the parameter space, like what are the values that we choose as the baseline. Also, it fails to account for factor interactions, which is what happens if we kind of move and vary multiple factors at once, right? This can lead to different behavior than just varying them independently. And also, we usually don't have the analytical derivative, but this can be salvaged pretty easily by just using the discretized derivative, right? We can always do that, and aggregating over multiple sample points, to filter out the dependency of the initial point. And this way we get something that's called the elementary effects method, which is a nice method often used for screening. That means kind of leaving out or detecting which variables are not quite as important and leaving them out. But the kind of standard methods with some nice mathematical background are the variance-based methods, where the main idea is to compute global statistics, that is, expected values and variances with different parameter combinations fixed. I have the equations written here just so you have an idea of how such a thing can be defined. But what's arguably more important is their interpretation. So on the left-hand side, I have the first order sensitivity index, which tells us how much of the total variance is explained by changes in xi alone. So kind of like in the one at a time scenario where we just move one factor around and see what happens. And we get the exact percentage of variance, which we can kind of control in this way. But this still fails to account for the factor interactions. And for that, we have the total effect index, which tells us how much of the total variance would be lost if we left xi out. So this contains the first order, but also higher order interactions where we get like pairs or triplets of inputs that contain xi, and we also get a percentage of variance, which somehow depends on xi. Now, there are multiple methods to estimate these, and we'll see one of them at the case study, but for now, that's enough with the theory. But before we get to the case study, I have just a brief overview of the topics that sensitivity analysis has been used for in pedestrian and evacuation modeling recently. First of all, we can use it to kind of study the parameter sensitivity and simulation models, so how the simulators themselves behave, or we can use it as a tool for model validation, or we can use it as kind of the main tool of analysis to study the model behavior, or we could do uncertainty analysis and kind of assert how confident we are in our results. Now, I have a bunch of references here, which I will show you at the end of the talk in case someone wants to pause and take a look. But for now, we can get to the actual case study. So as I mentioned, we'll have a simulated evacuation of a heterogeneous crowd, where the problem is we want to study the total evacuation time of a cramped interior room with respect to the seating arrangements. So we'll be looking at who is seated where and what effect that has on the total evacuation time. So the premises are fully occupied. That means each seat is taken and some occupants are movement impaired. In this simple case, this is simulated by simply a slower speed, a longer acceleration time, and a larger diameter. And what we want to do is estimate the sensitivity to the number or ratio of movement impaired occupants, which is kind of like an extrinsic variable, which is given to us from the outside if we're, for example, organizing an event. And then we have two descriptors of the seating. So we have the average inter-occupant distance of movement impaired occupants, which basically tells us whether the movement impaired occupants are kind of close together in a single cluster, or if they're more spread out evenly throughout the room. And we also have the average distance to the exit of movement impaired occupants, which is pretty much the average distance that they have to travel to exit the room. And as I mentioned before, this is a simulation study, so the simulator of choice here is Pathfinder by Thunderhead Engineering. Now, what geometries are we working with? So we have a train geometry on the left-hand side and a lecture hall geometry on the right-hand side. At the top, I have some actual pictures from inside of the model geometries, and and at the bottom, we have their Pathfinder models. So in this case, the kind of brightly colored occupants are the movement impaired ones, and the darker red-ish are the non-movement impaired occupants. Okay, and now with the uncertainty analysis. So here we are asking the question, whether is it even worth it to study the effects of seating on evacuation time? And what I hope to convince you is that the answer is yes. So one of the tools that we can use for this is the so-called law of total variance, where we can decompose the total variance in total evacuation time to an unexplained variance portion, which is basically the inherent randomness of the model, where if we run the simulation multiple times with the same seedings, basically, we get some different numbers based on how, in that particular case, the occupants act. And we also have an explained variance portion, which is sort of the deterministic part of the equation, given a fixed seating configuration, which I called C here. And we can estimate these numbers quite easily just from the definition, and we will get a table like the one below, in which I've computed 50 randomized seating configurations and executed each of them 50 times, with approximately 20% of the occupants having some movement impairments. And from this table, we can see that for both geometries, we get something close to 50% of unexplained variance and 50% in the explained variance, which is a bit less for the train geometry and a bit more for the lecture hall, which means that something, in this particular case, something like 50% of the total variance is actually attributed to just the seating. So on a closer look, we can look at the individual distributions where for different seating configurations. So here I have extracted the fastest and the slowest seating coordination for both the train and the lecture hall scenario. And we see that the distributions are quite different. On average, the difference is something like 7 seconds, which is definitely not negligible. And if we could figure out what characteristics lead to these faster distributions, we could obviously salvage that and use it while, for example, designing seating guidelines. And there is also one more caveat here, in that this all very much depends on how accurate those estimates of the averages are, right? So here I have just as kind of an illustration, the convergence plot of the estimate of average total evacuation time given the number of samples used to compute it. And we see here that for the first like 10 or so samples, the estimates are actually quite volatile. So this is something that we should always keep in mind, right? For further analysis to filter out the randomness, I've chosen 10 as the number of samples, which is reasonably close to the total values. But as I said, it's something to always keep in mind. And for illustration, I have the fastest and the slowest configurations extracted here. The fastest ones at the top, we can immediately see that the movement impaired occupants are near the exit here, so that don't have to travel long. And in the slowest ones, it's kind of the opposite here, right? They're far from the exit and kind of close together, but not in like a very noticeable cluster. Okay, and we can put this into numbers by the sensitivity indices that I've talked about earlier. So we can estimate those total effect indexes and the first order sensitivity indexes by what's called Saltelli's method. And I used a Python implementation here in SALib, where we can see that from almost 13,000 model evaluation, we get the following numbers. So we can see that the main driving factor is this N here, that is the number of movement impaired occupants, which is kind of the macroscopic variable that dictates the average velocity of the entire crowd, right? But we see that the seating characteristics are not exactly negligible, especially the exit distance amounts to something like 25% of the total variance, or 23 in the cases of the lecture hall, which is definitely not something that we can just discard, right? The inter-occupant distance is not nearly as important, especially in the first order index, but we still get something like 10% of the variance in the total effect index. And actually, the difference between these two numbers means that these factors interact with one another, which is something we would miss if we just used one at a time approach, which is very common. So the bottom line is that this is worth further study, and we should pay more attention to it in further research. I've also talked about how great all of this is, right? But there are, like with anything, there are limitations and things to consider, mainly that these variance-based methods are very computationally demanding. We see on the graph here a clear exponential trend, which is given by the method used to estimate these indexes, where each time we want a more accurate estimate, we need to double the amount of samples that we use to compute it, which is clearly an exponential trend, and that might be limiting. But there are, of course, ways to remedy this. For example, we could use screening methods like the elementary effects method that I mentioned earlier to eliminate some of the variables that don't have a big effect. Or we could build a surrogate model, which is basically a machine learning model, and you test the sensitivity of this model instead, which is fast. Or we could parallelize the computation, which shouldn't be hard, given that we get a matrix of inputs, basically, that we can process independently. Another thing to consider is that the results depend heavily on the distribution of the parameters. So, for example, for the ratio variable before, I chose a uniform distribution between 10% and 30%. But if I chose a different distribution here, then we would obviously get different results. So this is also something we should keep in mind. And of course, any findings still need to be empirically validated. So for example, we haven't found a large effect in the clustering variable, but that doesn't mean that it does not exist. Maybe we just didn't model it properly, right? So also something to keep in mind. And now to conclude, in the first part, I've told you something about sensitivity analysis, and it is a powerful tool that is starting to see use in evacuation modeling, and paired with uncertainty analysis, it can provide great insight into the behavior of our model. And from the case study side, uncertainty analysis shows that roughly 50% of the variance in total evacuation time can be attributed to the initial positions of movement impaired occupants in this particular setting, and some seating configurations lead to better performance. And while the macroscopic composition of the crowd is the main driving factor, the effects of initial positions are non-negligible and definitely worth further study. So obviously, I've kind of simpled this down to some of the main key factors, but there are more details, obviously. For example, what distributions we choose for each of the parameters, or how do we generate such configurations that have these properties, right? So these are all things that are worth taking a closer look at. I have some links here to this case study and to sensitivity analysis as a whole, in case anyone wants to look. And here are also those promised references in case someone wants to pause the recording and also take a look. And with that, I thank you for your attention, and I'll gladly answer any questions or take any suggestions, but I guess that's after the second speaker gets their turn. So thank you again.
Thank you very much, Juraj. Thank you for a great talk, and for the references at the end. I really am happy that you put those as well, because I think there'll be people who are interested in following up. So yes, absolutely. We'll hold the questions until the end. I'd like to just invite Yuxin to share your screen, please. And thank you for also staying on time, Juraj. And then we'll have plenty of time for questions. So I'll turn it over to you, Yuxin.
Does that look good?
Yep, we can see your screen. You just need to put it in
Full screen?
full screen. Yep, we can see that. Great, thank you.
Okay, so I will start. Good morning, everyone from Europe. Well, it's like good afternoon here from me in Asia. It's like 3 o'clock now. And I'm Yuxin Zhang. I now work at the Hong Kong Polytechnic University. I'm a research assistant professor here, and my research field is about like human behavior in fire involving like virtual reality in evacuation choices and also evacuation modeling and some smart evacuation system. And maybe I would like to advertise me for a bit. If you are like a PhD student and you want to visit us like within 6 months, like 3 months or 6 months, and the Hong Kong Polytechnic University has very good scheme for the scholarship and those visiting programs. So if you are interested in it, just drop me an email. And today I'm going to talk about something about how to model evacuation behavior in fire. And I will introduce a coupling numerical approach using both computational fluid dynamics for fire development and cellular automaton for the evacuation modeling. The content will be composed of like 4 parts. The first, I will introduce about some basic knowledge and for the fire development and evacuation modeling. And second, I will introduce the coupling model using CFD and cellular automaton model. Then I will introduce a demonstration in a tunnel fire as my previous work. And the last, we will discuss something about the limitation and the future work. Let's start from the evacuation behavior. Well, in fire safety design, we have we have 2 important concepts called ASAT and RSAT. The ASAT is the available safe egress time, refers to the time fire ignition till the whole environment is no longer suitable for people to move through. And RSAT is the required safe egress time, well, refers to the total time a person needs to evacuate. As long as ASAT is larger than is smaller than ASAT, then we could ensure people could evacuate safely. However, the timeline is quite simple, but things will get more complex if the timeline is combined with like 2D or 3D space, because people's movement and their choices will be largely affected by fire. As we could see from this slide, well, evacuation movement could be simply or like clearly modeled by some like platforms or softwares. However, the CFD model, the fire development, will pose a very important effect on people with like different temperature or visibility and even those thermal radiation and toxic gases. So how could we evaluate or like add those impact on people? Then we look at the fire development. The fire development could be easily modeled by like some software like FDS, and we just mesh the whole space into those several grids, and we use the Navier-Stokes equation. And those modeling could present us a clear figure about how those like fire develops with like temperature, or we could have the visibility, and then we know that how it works. Then we want to add those impact onto the cellular automaton model so that we could find how people move with the impact. Thus, we choose like cellular automaton model. It is a regular grid of cells, and each in one will have a finite number of states, such as on and off, or like occupied by person or empty. And the grids can be in any finite number of dimensions. Like we have 3 common sides. The first is more neighborhood. It has 8 choices. And the second have 4 choices. And the third one, hexagonal grid choices, they have 6 ones, and they have the same distance, which is very popular these days. However, we want to consider the fire development at the same time, so that we could only choose this one, the more neighborhood, because the CFD meshing is the rectangular grids. And in this way, we could put them into the same grid, and thus we could have their impact together. With this discrete space, and we have the discrete status, this kind of cellular automaton model could have a computational speed very fast, so that it is applicable to those large-scale buildings, and is also easy to define by the users. In this way, we could find that we could divide the whole space into several grids. And for some grids, we generate some occupants. And those occupants will be influenced by the fire development, and they will move to their adjacent cells from one time step to the next time step. In this way, we could build a framework of fire evacuation model. Firstly, we use the CFD model to get the fire development, and we extract those parameters like temperature, visibility, etc., and couple to the cellular automaton models. The cellular automaton models, those people in the models will follow the predefined moving rules, and the moving rules will update time by time according to the fire development. In this way, we will have a coupled evacuation model. So this is a detailed flow diagram of the coupling fire and evacuation model. For the preparation work, we build the 2D or 3D structure model, and we import the model both into the FDS software and the CA model. For the FDS models, we do the configuration, grid meshing, and fire scenario settings and start the modeling. And we will extract the key parameters, including those parameters which will affect people's movement at each time step, and store it. And we will go on the fire simulation until the time reaches the threshold, and we will end it. During the same time, we will generate occupants and other like axes or the obstacles in the cellular automaton model. Firstly, we will formulate a predefined moving rules without fire and for evacuation movement. And then for each time step, we will import those key parameters and calculate the force on each grid and update the predefined moving rules and calculate each occupant's aim and their destinations. With this iteration, we will calculate if all people evacuate or if no available cells for people to move. And this is the diagram of this coupling CFD and cellular automaton model. There are some key elements of the evacuation modeling and the predefined rules. For example, we have the goals at the exits. Suppose we have two exits here as a case, and the obstacles are the fire source. And also we will have other obstacles if it's a building and they have walls or doors. And the potential movement, we follow the mall neighborhood, which means they could move to the 8 agent cells or they could stand still. And for the attractors, we have the social influence by nearby agents, and they are also attracted by the axis. And the repellers, we consider about the social influence is they are too near, and also the fire range, which means like near the fire source, they will have high temperature, will repel people to move close. However, they will not a huge threat to people. And the exact moving rules in my framework is defined as this. For the attractors, we consider attraction and alignment. And for the repellers, we consider fire, cross, and nearby agents. For this rule, it's just a case or like an example. And the attractors and repellers, especially about their coefficient, should be adjusted for specific cases. Below is a demonstration in a tunnel fire to see how the framework works. I use a tunnel standard section as a case, and this section is like a 200-meter length and 10-meter wide, and we set a fire source in the middle of the tunnel with 5 megawatt, and we have 2 axes with 100 in distance. We could see from the FDS modeling results that this is the top view of this tunnel with 2-meter height. And from 50 seconds to 350 seconds, the temperature is increasing and the visibility is decreased, which means the central part near the fire source will be not available for people to live. In this case, we could investigate like the axis layout or other things to optimize the tunnel fire safety. For example, we investigate the exit locations. And here we set 7 types with the standard one, and we have a wider exit. Then we choose type 3 with 2 exits with 100 meter in distance, and 2 narrow exits, 2 further exits, and 2 types of opposite exit. And with this evacuation framework, we get the evacuation time and the successful percentage for those 7 types. And we set 4 cases, like the low density of occupants, middle density of occupants, high density. And we also investigate that the high density of people, where we do not set a fire so that people could move freely without the influence of the fire's obstacle. And for those 7 types, we get the results that the type 7 has the shortest time and also with a high successful percentage, which means this kind of design is more beneficial to people's evacuation. We could also compare those 2 curves about the blue line and the rose line. We could tell that without fire, the evacuation time could be very quick, so that it means if we do not consider the fire during the evacuation, maybe we will get a much more optimistic result and will cause potential injury for people. We also use it to investigate the effect of signages. We investigate 2 kinds of signages. The first is the static signages, which means the signage points to the nearest exit. And the other one is the dynamic signages, which means when a fire occurs in front of one exit and it will block this exit, there will be a red cross show this exit is not available. And we have some assumptions, like a few people will move to the nearest exit, but they will find other exits if this one is blocked. We also consider like the social influence, like those kind of information. For example, this exit is not available, will spread among people. And we want to know if this kind of dynamic signage will have positive effect on evacuation. Here are the preliminary results about the evacuation time. And we have like 8 scenarios. The first 4 on the left part is the 4 densities, and they are without the signage. And the next 4 is with the signage. If we take the solid curve and the dash curve of the blue color, we could see that when the social influence increase as the x-axis, the evacuation time will increase. It means that sometimes social influence may spread the wrong information and will delay people's response and their movement during the evacuation. And we could make a contrast and see the right part with the dynamic signage. And for the blue curve, it is a apparent decline of the high density with signages with this kind of dynamic signages. That means in this kind of simulation, the dynamic signage shows that exit A is not available, will spread among people, and this will increase people's evacuation speed. Those are the above are the demonstration in a tunnel fire. Well, this framework is proposed. It has a lot of limitations and some future work. We will do more about this. Firstly, as I said, that the cellular automaton model is a discrete methodology, so that the computational speed is quite fast. However, the FDS simulation sometimes for fire may cost like several hours or several days. Therefore, the real-time evacuation prediction is not available. Thus, in our group, we do something about using artificial intelligence with those data and the image to predict the fire development, so that with this, we could have a faster speed of the cellular automaton model. And the next key problem is the validation of this proposed model. And we are considering 2 approaches. The first is to conduct full-scale evacuation experiments with fire, where we still suffering those ethical problems. And the second one, we could compare with previous models so that we could see if it works well. And the last thing we are considering is to combine the evacuation prediction with those like digital twin system, because we could have an accurate and fast prediction of people's evacuation and their movement. We could have a great estimation of people's distribution, especially in those large buildings. And then we could build an emergency digital twin system to show where people are. And above is all the content about this sharing for today. And I'm very honored to introduce the evacuation modeling with the CFD modeling and the cellular automaton model. And this is just a very basic work at the very first few steps. And we need more work in the future to validate if it works and to refine and to do more collaboration in the future. Thank you all.
Thank you. Thank you both. Really appreciate your presentations today. So I have a few questions, but I see one in the chat. So we've got some claps as well for you both. So for the first speaker, the question in the chat reads as, can we use sensitivity analysis as a tool at a much broader level to identify which variables are most important for different types of evacuation scenarios and applications? For example, a road tunnel, a station, a theater, i.e. to run this type of analysis on many scenarios so that we know beforehand where to put our efforts in model input calibration, for example, pre-travel, flow constraints, etc.
Yes, thank you for the question. So, yeah, the sensitivity
the question was from Enrico. Sorry, I should have mentioned that. So,
thank you, Enrico, for the question. So, the sensitivity analysis is a very general kind of topic that we can employ to pretty much any scenario we think. There is one small issue maybe with discrete inputs, which if we have different like categorical variables such as types of scenario, it might maybe just be easier to use standard statistics, right? Because there is no, these variances often kind of use a ordering of the variable, right? Where they're very well suited to continuous variables, but with discrete cases such as these, we might just be better off using standard statistics, right? But if we have like continuous descriptors of the type of scenario, for example, then yes, sensitivity analysis is, I think, perfect for these use cases. Or if there's the type of, or the problem of detecting the most important, or we could filter out for example, using the elementary effects or other screening methods, there are plenty. We could basically filter out the variables which do not have like a significant effect. And those methods are designed to be very efficient in the sense that we do not need too many model evaluations. So yes, I think definitely we could use those, but it's important to kind of keep in mind if we have a discrete variable or a continuous one in this case.
Okay, great question. My question is for you, Yuxin. Maybe it's a couple-parter. So I was just curious. I mean, obviously you've developed this framework with the CA model, and when you develop a framework like that, you know, you have to sort of, you're starting with your own assumptions and data, and I kept sort of asking myself a couple of questions. Maybe I'll start with the first one. So why develop your own framework? Does nothing else exist that can provide you what you're looking for, coupling the fire with the, you know, people movement and human behavior? That's my first question. And the second question is, you talked about validating, which I was really happy to see that. But then you talked about validating with real data, and then you talked about the ethical issues, so that's good. So I was wondering why you didn't mention potentially using VR for validation.
Okay. Thanks, Erica, for your questions. Those are also the questions when I start to work this field myself. And the first question as to why to for this framework, it starts like from the I think the last FEMTC conference when I spoke to the engineers in Pathfinder, which Pathfinder is one of the most common software we use for evacuation modeling and calculation. And they also have the PyroSim, those software, which is the graphic user interface for the FDS. And I asked them why you don't put them together so that you could consider the influence of fire on people's movement. And their answer is that maybe they have more work or like a couple of years to develop this function. And I know that the FDS and EVAC, which is I think was developed by a research group in Finland, they proposed this kind of function with the FDS, and it works well at some point. However, I tried to use this software, and I found I don't know quite sure they didn't update it for like several years. So there's some most recent findings about like how people behave with the fire's influence is not involved. So that I'm thinking if I could like develop or write my own code so that I could evaluate the influence of fire on people during the modeling process. And then that's the start of this work. And also with the development of FDS and the Python function, we are now able to extract the key parameters of the fire development in real time in each time step of FDS, so that we could extract the in 10 seconds or in 20 seconds, we could know how the fire will develop or spread, and then we could import those data to our model. And the second question is about the validation one. And VR is a extremely good suggestion for the validation, and I will consider to use virtual reality to the validation in the future. I just missed the virtual reality aspect here. Thank you.
Thanks for the comments on that. I think the one thing that I just kept thinking about when you're starting from scratch and you're having to put all of the behavioral aspects, it's for like a model developed at Greenwich. They've been modeling that for many years. They've got a signage model in there. They've got this sort of interaction, at least on some level, with the fire. So it's hard to start from scratch when some of these other models that exist have been in development for many years. But thank you, Yuxin.
Yeah, that's true. Thank you.
So we have some other, okay, great. So one question for the first speaker and then another question for the second speaker. Nikolai, would you like to say your own question, or would you like me to read it out?
No, sure, I can say it. Hi everyone. Great talk, Juraj. Really
Yeah.
interesting. Thank you also, Yuxin. Great talks. So anyway, my question is just about the use of surrogate models. And obviously these are really interesting and a really promising idea. I'm just wondering, in Juraj, what you think, whether you might not just need the same amount of compute power to construct a good surrogate model for a complex crowd model as you would to do the sensitivity analysis in the first place?
Yes, thank you for the question. So I had a study it's actually in one of the linked references there, where I had something like 9 variables or so. And in that case, the computation time needed to analytically kind of estimate these was just too much. It was prohibitive. So I did a surrogate model there. And this is one of the exact things that I tested here. So I had like a larger estimate with of the analytical approach with, I believe, 128 or so samples, and that's times the number of variables and times some other constants. So that was like a large data set, and I trained some surrogate models on that, and it gave me some numbers, which I think were really good. But then I tested this same thing, but just on a very small sample of the data set, which had something like 256 times smaller number of samples, and the results were actually very similar. So In that case, we could just use a very small sample of the data and train a surrogate model. Obviously, that depends on whether the function is, or how nonlinear it is, what kind of surrogate model we choose. But in that case, the results were very similar with many times smaller data set. And one more thing that I did in that study as well was that I first employed the screening method, right? The elementary effects, which also requires us to run the model a couple of times, but that's comparatively a lot faster than the other methods. And so we also end up with a data set, right? And we could also train the surrogate model on this data set and kind of dodge the entire the expensive computation, right? And it turns out that those results were also similar. So basically, whatever data we can use, we should use it. And in general, it would still save us quite a lot of time, but obviously that depends. If we had a model like a neural network or something that's very complex and requires a lot of data to train, then yes, it would probably be more expensive than to just estimate the statistical way. But for like reasonably complex models, I think it would still save us a lot of time. And for anything more than like 3 or 4 variables, I think this is the way to go. So yes, that's a great question. Thank you.
Can I follow up? Is that all right?
Yes, of course.
I don't know. Erica, am I allowed?
This is a very quick question because we have a few more for the other
I'll leave it
speakers.
to later. Thank you.
Oh, don't want to cut you off, Nikolai. Go ahead, please do follow up.
No, really. I just go into surrogate model discussion. It's fine. It's fine. Honestly, let's move on. Let's move on.
Fair enough. Okay, the next question is from Enrico for you, Yuxin. Why are you using a CA model rather than a continuous modeling approach? While computational time is an advantage, results are often very sensitive to the grid adopted.
Thank you for Enrico's question. I will share some of my thoughts when I developed this framework. Well, maybe we could also consider to use like continuous modeling, like social force model. At the start, it starts from the grid meshing of the FDS, because the FDS, they mesh the space into several grids, and like with the set like 0.4 meter and 0.4 meters, and it's exactly like similar to the body size of persons for the cellular automaton models. So it's very possible to mesh them together so that we could get the results of the FDS for each grid, and then we could import the results to the CA models. And for the FDS models, actually the results are not exact because they use the interpolation for their file development, so that they could only get the results for each grid, and thus we input those results onto the cellular automaton models. And this is the first reason. And the other one is that I started from for the framework for a whole tunnels design, or like the optimization, to test if the fire safety design or like the evacuation design is enough or not. And for the continuous model, actually the computational time sometimes is still long, like but the cellular automaton model, especially for those like large scale building or like a complex, underground complex or a metro station, which are much faster. So that at this time I choose the cellular automaton model for both the grid meshing and the computational speed. But for the following work, and also as Juraj says, that the sensitivity analysis, and I will consider like if we could mesh the grids in a smaller scale, like the 0.1 meter, multiple 0.1 meter, and for one person will occupy like 9 grids or 16 grids, and see how it works, and if the results are aligned with each other. And maybe we could test if the sensitivity analysis is fine with this setting. Thank you. And is it good for you?
Yeah, I guess it's mostly computation and ease of implementation, the main driver. So that's what I guess indeed. Thank you.
Thank you. I will try, but anyway, I will try the continuous model because they are the two mainstream of the evacuation modeling.
That's good. I also had the same sort of thought as Enrico, so I think it'd be good to try the continuous approach. Last question, Simon. I'm happy to read it. Okay. If you wanted to read your question, or if you wanted me to read it, up to you.
Okay, thank you. Thank you for the great talk. I'm a big fan of considering uncertainties in simulations, so I appreciate your ideas. I would be interested in the stochasticity of your model. So I assume that the crowd model that you used introduces stochastic effects. So if you repeat a single simulation for the exact same input, you get different results or slightly different results. And if this is the case, how do you account for this when running a sensitivity analysis? Because this kind of uncertainty would propagate into the results, right?
Yes, that's a great question. Thank you. So I believe this is still an active area of research here, because the sensitivity analysis models, they generally expect a complex but deterministic model. So far, there exists some Bayesian, I think, models that kind of try to use all the data that we have, but the methods that I presented here, the standard approach currently is mostly to just average out, or try to average out as much of the randomness as we can. So we work not with the actual like random variable, but with the average or the estimate of the expected value. But yeah, that has quite a lot of problems, mostly that, well, we lose some of the information, right? By kind of dropping the uncertainty. And this makes the models so much more expensive to, or these methods so much more expensive to evaluate, right? So in my case, I ran the simulation with the different, I believe, random seeds and whatnot 10 times and averaged it to kind of get an estimate of the expected value. But this is not perfectly efficient, and this is one issue that I hope to tackle in the future, right? To make use of as much data as we have and do not throw away the information about the uncertainty, because that, as you said, that might be significant and might affect the results completely. As kind of a stand-in for this, there's the law of total variance kind of uncertainty analysis that I presented, just so we have an idea of how large the effect of the inherent randomness is, and kind of look at it from two different ways. So the uncertainty analysis is one thing, and we get an idea of how strong this effect is. And then for the sensitivity analysis, we kind of just work with the averages, right? And we kind of omit the randomness from the model, which is kind of unfortunate, but it's the current general practice right now. So that's something I hope to address in the future. Thank you for the question.
Thank you.
Well, I'd like to thank you both for your presentations today. I also would like to thank the audience for coming along and asking some really fantastic questions, and making our speakers think a bit today, which is good. There is another chat from Nikolai for you, Juraj, so you might want to take a look at that before we end today, and maybe you guys want to have some chatting offline about sensitivity analysis. So I want to thank everybody today for coming, and this has been recorded, and this will be up on the YouTube channel. Hopefully, if you're not already a member of our group, you'll consider signing up and getting involved, and look for the next webinar series after the summer has come and gone. So thank you all, thank our speakers, and have a really great day. evening, afternoon, wherever you are. It was wonderful to see you. Thank you.
Thanks, everyone.
Thank you so much.
Thank you.
Thank you, Herman.
Thank you, everyone.
Bye bye.